Let's look at the sum to infinity of a sequence. Now, what that means is that you have an infinite number of terms lined up and you add them all. Now you might be saying, but if you have an infinite number of terms lined up and you keep adding, you would get an infinitely large answer. But that's not in all cases. Alright? Now, the fact is, if you try to find the sum to infinity of an arithmetic progression, then you get an infinitely large answer. Example, if you have, let's say, an AP, the first term is 1, the common difference. If the common difference is 1, the first term will be 1, then the next term will be 1 plus 1, which is 2, then 2 plus 1, which is 3, 3 plus 1, which is 4, 5, 6, and you keep adding them up. The numbers keep getting larger and larger and larger. So, you cannot add an infinite number of these and get a fixed number, get a finite number. It would be infinitely large. Now, if you have a negative, what you would have, if you have a negative d, what you'd have is 1. Then you would have, the second term would be 1 minus 1, which is 0, plus the next term would be 0 minus 1, which is negative 1. So you would have 0 minus 1. Then the next term would be negative 1 minus 1, which is negative 2. And minus 3, then minus 4, then minus 5. So you would still have an infinitely large number. It's just that it would approach negative infinity. Even if d is a fraction, small fraction, for example 0.1, you still have an infinitely large answer, right? The sum would approach infinity because you'd have 1, then 1.1, then 1.2, 1.3, and it will go up and up and up. So if you add these, 1 plus 1.1 plus 1.2 plus 1.3 plus 1.4 plus 1.5, because you keep adding 0.1, you add 0.1 to 1, you get 1.1. Add 0.1 to 1.1, you get 1.2, and so on. So these numbers, they themselves are approaching infinity. And you keep adding, and the number would get larger and larger and larger. Alright? So, when it comes to an arithmetic progression, you always have the sum approaching a larger and larger or smaller and smaller number. They would be approaching positive infinity or negative infinity. So with an arithmetic progression, that's out of the question. You cannot sum an arithmetic progression to infinity and get a finite answer. Let's check out the GP, geometric progression. If you have, say, a geometric progression, first term is 1. And let's say the common ratio is 1. You would have 1 plus the second term will be 1 times 1, which is 1, plus third term will be 1 times 1, which is 1, plus 1 plus 1, and it goes on and on. The fact is, the sum would approach positive infinity. Alright? So, let us try with our common ratio greater than 1, say 2. You start with 1, then 1 times 2, which is 2, 2 2 is 4, 4 by 2, which is 8, 8 by 2, which is 16. So these terms would also approach a positive infinity, an infinitely large answer, right? Now, if you try another way to make the 2 a negative, what you would have is 1, then 1 times negative 2, which is negative 2, negative 2 multiplied by negative 2, which is positive 4. To get the next term, you multiply positive 4 by the common ratio negative 2, you get negative 8. To get the next term, you multiply the negative 8 by the common ratio negative 2, you get positive 16, and you keep adding. But here, you still have the sum approaching an infinitely large answer, because the number itself, is getting larger and larger. However, there is one situation where you can actually have an infinite number of terms of a geometric progression, and you add and add and add them all, and you end up with a finite answer. What happened here is that the r must be less than 1. The common ratio must be less than 1. For example, if you have the first term, let's say the first term is 1, and the common ratio is 0.9, then you would have 1 plus 1 by 0.9, this is 0.9 plus 0.9 by 0.9, which is 0.81 plus 0.81 by 0.9, what is 0.81 by 0.9? Basic mode, 0.81 times 0.9 would be 0.729, 0.729 plus, and you have 0.729 times 0.9, so that times 0.9 equal 0.6561, 0.6561 plus, and you see that each time the next term gets smaller and smaller and smaller and approach 0. So you will get a finite number for this. You can imagine that you have, let's say, a length of string 1, and you cut the string. This is 1 meter. You cut the string so that you remove part of it and 0.9 is left. You add it to the length before. Alright, so this was the length before. Then you cut the string again to make 0.9 left, which is 0.81. And you add it to what you had before. Then you have 0.81 reduced by 0.9, and each time there's a reduction in the length of the string. The string gets shorter and shorter. You keep making the string shorter and shorter by 0.9, all right? The fact is, when you take all these lengths of strings and add them up, even if you keep dividing down the string into 0.9 forever and ever and ever, when you add them up back, you will get a finite number, all right? You're going to get a finite number. Another case might be this. you have a geometric progression where A is 1 and let's say R is half. It's like you have a string, right? Let me have my string in a straight line. That's 1 meter long. You cut it into half. That's half meter. The half that you had, you cut it into half again. Then into half again. Half again. And you keep halving the string. When you add them all up, what are you going to get? Let's see. 1 plus half plus this is a quarter. Half of a quarter is 1/8. Half of 1/8, 1/16. Half of 1/16 is 1/32. And so on and so forth. So, let's see, get an idea of what you might get when you add up these lengths of strings. You have 1 plus a half, which is 0.5, plus a quarter, which is 0.25, equal, all right, plus 1/8 plus 1/8, close bracket, equal, all right, plus, open bracket, 1/16, equal, all right, plus 1/32, open bracket, 1/32, plus 1/64. Half of 1/64 is 1/128. So you plus, open bracket, 1/128. And you keep going and going and going. Actually, you will reach a point where you realize you're approaching 2, getting closer and closer to 2, but not reaching it. So if you should keep doing this forever and ever and ever, you get very close to 2. So what happens is that if you keep adding 1 plus half plus a quarter plus 1/8 plus 1/16 plus 1/32 plus 1/64, on and like that, the answer will approach 2. So basically, once you have the common ratio less than 1, then you can find the sum to infinity. All right? But the thing is, what is the equation for the sum to infinity? Let's see something here. From previous work, we saw that the nth term, an, of a geometric progression is a times 1 minus r to the n divided by 1 minus r. Now, if r is less than 1, what would r to the n be? Now you will find that when r is less than 1, right, and you have r to a large power, r to that large power will be a small number. For example, if r is 0.9, all right, 0.9 to the power of 2 would be 0.9 by 0.9. Let's use our calculator. It would be 0.9 times 0.9, which is 0.9 squared, which is 0.81, times 0.9 again, which is 0.9 cubed, 0.729, times 0.9 again, which is 0.9 to the 4th, times 0.9 again, which is 0.9 to the 5th. Do it again, this is 0.9 to the 6th. Do it again. This is 0.9 to the 7. 0.9 to the 8. So each time the answer gets smaller and smaller. Alright? You went to 0.729, 0.65, 6.59, 0.53, 0.478, 0.43. So it keeps getting smaller and smaller. If we put our calculator in advanced mode and we find 0.9 raised to the power of 10, we get 0.348. What about 0.9 raised to the power of 20? What do we get? 0.12. So the number keeps getting smaller and smaller. If we have 0.5 times 0.5, that's 0.5 squared. It's 0.25 times 0.5 again, 0.5, which is half to the power of 3, 125 times 0.5 again. If we have that times half, we get 0.0625. So each time we're halving the number. So you will see, for example, that 0.5 raised to the power of 10 is very small. 0.5 raised to the power of 15, even smaller, it's approaching 0. So you keep multiplying a certain number, is a fraction less than 1. When you keep doing that, multiplying it by itself, each time the answer gets smaller and smaller and approaches 0. So when n is very large, r to the n approaches 0. So what you get is a 1 minus 0 over 1 minus r, which is a over 1 minus r. So the sum to infinity, let's use this symbol for infinity, is equal to a divided by 1 minus r. Alright? So basically, the only sequence that you can add to infinity is a geometric sequence when the common ratio is less than 1. And the formula for that, sum to infinity, is a divided by 1 minus r.